So what we're looking at here is now our chemical reactions. So we should have a pseudo basic idea on how to balance chemical reactions. The next layer to this is that when we look at a chemical reaction, we need to be able to predict, or rather classify it according to the category. So we've got 6 categories of our chemical reactions listed out here as our general forms. These are supposed to help you organize when you look at a bunch of formulas for a chemical reaction, so that you can then kind of piece it together to classify them out according to their chunks. Right? This does not mean that the ratios are the same. So I'll get students sometimes saying, well, it's not a single replacement because it has, a metal. That's a horrible example. It has a metal and then it has a non-metal, but the non-metal, there's 2 of them, and this formula says 1. These are not numerical organized at all. Right? This is just grouping those classifications, so don't start throwing numbers into it per se. There is one exception, and that would be at the very, very bottom of the list over that way. That would be our combustion reactions, and those formulas are going to hold pretty true for the most part. Okay? The one formula that wouldn't be would be the part that says X and Y, because X and Y aren't numbers, but those could mean any number. Okay, really? The rest of the formula will hold true. The amounts, or how many CO2s get produced or how many waters, that can change, but water will always be produced and CO2 will always be reproduced. The other piece that's important to acknowledge behind these chemical reactions is that you will be responsible to predict what the products are for those last 4 reactions. So single replacement, double replacement, neutralization, and combustion, you need to predict what the products would be. So if I just give you the reactants, you have to be able to say, well, based on that information, it's going to be these products. Okay? That can be a little bit more challenging. That's the kind of practice you should be getting into. The combination and the decomposition, you are not responsible for predicting them. The play pause it slide, I know, started to show up some patterns, and the textbook shows some patterns as well. Those patterns you're not expected to memorize, so don't worry about that. Be more cognizant of the fact that there are patterns. You just don't need to know them. Okay? What you need to know is how to classify them. Okay? With that, let's take a look at our combination reactions. This would be the exact kind of slide that I was referencing, because there's categories for combination reactions. All too often, people look at this and say, oh, I've got to memorize it. I don't want you to memorize it. I don't. They're just categories to help you kind of classify if you so chose. So I made a slight addition to this slide and say, ta-da, don't memorize those. Okay. You do need to memorize that part up at the top that has not been blacked out or crossed out. That is important. You do need that. Okay, so you are responsible to balance and identify it. You are not responsible for predicting your combination reactions. With that, let's take a look at an example that I thought I was going to have put up there, but I didn't actually put one in. So let's look at one. Let's backtrack a little bit here so we can see some of those rules. Let's take a look at why we don't need to, or why we shouldn't just memorize these. We're going to take a look at that orange one. I'm going to react a metal and a non-metal. Okay, so the metal I'm going to choose in this case will be iron with a symbol of Fe, and that's a solid in its metal state. And I'm going to react it with a non-metal. I'm going to react it with oxygen. The formula for oxygen would be O2 gas. If I go through and run this reaction, those 2 pieces are going to combine, and we will end up with iron and oxygen. Okay, so now we're going to run into an interesting dilemma. Name this for me. Okay, that's that pause button. If you go through and do the name, hopefully you'll note that we get iron, we would get oxygen that becomes oxide, and then you'd have to specify the Roman numeral because iron was a +2 in this particular case. How do we know it was a +2? Well, according to the formula, there's 1 iron, I don't know its oxidation state, plus 1 oxygen. Oxygen is always a -2. This equals 0. I go through and solve, and I get X equals 2 plus 2, which in this case I said was the charge for the iron. Okay, so if I go from the name, I get this formula, like those are a pair up. But how do I know how much iron and how much oxygen should come together in this combination reaction? How did I know it was supposed to be iron 2 oxide? Because it could have just as easily been iron 3 oxide. And in fact, it's far more likely for it to have come out as iron 3 oxide. And if we were to come up with the formula for that, FeNO, iron's a +3. How many irons do I have? Plus, I don't know how many oxygens I have, -2 equals 0. And when I go through to figure that out, I end up finding out my formula is Fe2O3, different formula. So in this combination reaction, what should my product be? Okay. Should it have indeed been iron 2 oxide, or should it have been iron 3 oxide? Or for that matter, why not iron 4 or iron 6? Okay? And that's why you aren't expected to memorize or predict combination reactions, because there are certain cases that you don't know those charges. And the only way you would be able to predict it is if you knew the answer, which means you didn't predict it, you knew the answer. So that's why I say for combination reactions, don't worry about predicting. Given an equation or given names of an equation, you should be able to write out the combination reaction with the appropriate products, and then you should be able to balance. So in this case, for a quick refresher, iron 1 and 1, oxygen 2 and 1, that's not balanced, so I could put a 2 in front there. I changed a coefficient, so now I need to go back through and check again. Iron was 1 and 2, so that needs to become a 2. Oxygen is 2 and 2, so the oxygen's balanced. Again, I changed a coefficient, so I should check again. 2 and 2, 2 and 2, and it would now be balanced, okay, with each of those stages of my work being shown there. Okay? That is what I expect you to be able to do. I also expect you to be able to look at this equation and be like, aha, that is a combination reaction. And you would know it's a combination reaction because according to the pattern for combination reactions, we start with two things and they become one. When we go through and look at this, there's one thing, two things becoming one thing. Okay? That's the pattern I want you picking up with your combination reactions. Don't stress about predicting products of combinations. If you do one of the practice questions from the textbook is assuming that you look at the textbook to find the rules that are listed here. Okay, so don't memorize those. With that, we can continue on to our next reaction type. We also get our decomposition reactions. Okay, so this is where we start with a single substance and it becomes two or more. Again, I don't expect you to predict this because if we look at that reaction, what does it decompose into? Okay, one option is I could be like, well, KClO2 plus O2. That would be a decomposition. I could also have just as easily written KCl plus O2. Okay, and I would know that that was the answer because I remembered two video ago, maybe one video ago, that we talked about very briefly the decomposition of potassium perchlorate. Okay, so again, I don't expect you to have that memorized. What I expect you to be able to do is that once you are given the equation, come on now, did I have it? There it goes. Once you are given the equation, you should be able to look at that and be like, that's a decomposition. You should also be able to look at that and say, that equation is not balanced. This is how we balance it. Potassium, 1 and 1. Chlorine, 1 and 1. Oxygen, 4 and 2. To make that 2 into a 4, I need a 2 here. That makes that a 4. My oxygen is balanced. I've changed a coefficient, so I need to check again. Potassium, 1 and 1. Chlorine, 1 and 1. Oxygen, 4 and 4. My equation is balanced. I have a check where I didn't change any of the numbers. I'm now good. That's what I want you to do. Okay? So be able to acknowledge decomposition and be able to then balance the equation once you have it. Okay? They can't all be that easy. So for instance, the combustion reaction is a bit more challenging. You, I believe, saw this reaction in the PlayPosit, and you were asked to go through and balance it, and you might have struggled with it. So let's actually work through this one as a combustion. How do we know it's a combustion? Well, the absolute definition is just that it reacted with oxygen. But when we're talking about combustion in this class, really what we're referencing is the organic substance reacting with oxygen. And organic substances are things with carbon and hydrogen. When we have that organic substance reacting with oxygen, we produce always CO2 and water. So that's kind of cool. So now that we got our equation, we know it's a combustion, we can start the balancing process. Carbon, 4 and 1. I need that to become a 4. I do that by changing the coefficient. Move to hydrogen. Okay, I would typically do hydrogen first, and I don't have a good reason for that. But hydrogen and oxygen should be reserved for the end, which becomes much more important if you have to take a lot more chemistry. Okay, typically hydrogen and oxygen show up in a bunch of different locations, and that's what makes them challenging. So let's start. Hydrogen, 10 and 2. Well, that certainly doesn't balance. But if I have 5 H2Os, that 2 becomes a 10, and it would now be balanced. If we drop in our oxygen, we have 2 on the left. And of course, my technology is going to fight me on this, so I'll just have to talk through it while we're connecting. The CO2, I have 4 of them. Because there's 4 of them, I would have a total of 8 oxygens. The water has 5 water molecules, which would mean plus 5, which gets me 13. And here lies the rub. How do I get 2 equal to 13? Okay, that is a bit of a challenge, and there's really kind of 2 approaches to it that end up doing the same thing. Okay? The first approach is a purely mathematical approach. I would get 2 equal to 13 by multiplying the 2 by 7.5. For those of you screaming, but I thought you could only have whole numbers in a chemical equation. Yes, you can. So that means we would use that as kind of a placeholder for our work that would now take us to the next step. We would have to multiply that entire equation by 2. What does that mean? 2 times, 2 times, 2 times, 2 times. Okay? What's the end result in that? Okay? So we're now making changes again. If we look at our carbon, we would now have 8 carbons on the left-hand side, because 2 times 1 is 2, and that's C4H10. On the product side, 2 times 4 explicitly is 8, but there's only 1 carbon in CO2, and we would get 8. Hydrogen, 20. And 2 times 5 is 10, times another 2 from our H2O, we would get 20. For our oxygen, 2 times 7 halves. The 2's cancel, and I would get a 7. And then I would get, now we got to do math again, 8 times 2, 16, plus 10, 26. I really did the math horribly there, didn't I? Sometimes things go wrong. The idea behind this worked. I just used the wrong number to begin with. So what we're going to have to do is backtrack out of this. And I have to make sure I picked the right number to begin with. Okay, because for those of you doing the math, that would only get me 7 times 2, 14 oxygens. That didn't quite work. So yeah, 7 halves times 2 does not equal 13 for the record. That equals 7. I don't want to multiply by 7 halves. I want to multiply by 13 halves. Apologize for that. Hopefully I'll be able to flag it that I screwed that up in the video. Now we would go through, we need to get rid of that 2, so we can multiply everything by 2. So the methodology doesn't change. I just put the wrong number in. Carbon still comes out as 8 on the left and 8 on the right. Hydrogen comes in as 20 on the left, and it comes in as 20 on the right. Oxygen on the left, 2 times 13 halves is 13, but there's 2 oxygens in O2, so 13 times 2 gets me 26. Oxygen on the right, we have an 8, but there's 2 in CO2. 8 times 2 is 16. 2 and 5 is 10. There's only 1 plus 10 gets me my 26, and it balances. Those numbers do look very messy, so what we could go through and do is clean those up. 2 times 1 is 2. 2 times 13 halves is 13. 2 times 4 is 8. 2 times 5, 10. Okay? And that would now be my balanced equation. Okay? The other approach that we could go through and do, let's see if I can do it relatively fast, doing effectively the same thing. Okay, so for those people being like, God, I hope there's an easier method. Well, there is an easier method. Number 1, don't screw up the math. Okay, and then 2, it's not necessarily that much easier. But let's see if I can first get our numbers in here. We needed a 4 there, and we needed a 5 here for our water. Looks visibly correct. For our oxygen, we had 2, and then we had, counting the wrong ones, 8 plus 5, 13. When I encounter this issue where I'm getting an even number needing to be equal to an odd number, that doesn't work very well. It's usually centered on a species like oxygen. What do I mean a species like oxygen? It's diatomic. There are some other elements that aren't diatomic, but that are also equally complex. Sulfur can show up as that's an 8-membered ring. Okay, so you could see S8. So you could be running off of multiples of 8. So when you encounter this odd-even mismatch, look to the subscript of the offending element, okay, where it's all by itself. Multiply that subscript by everything. So 2 times 1, 2 times 4 is 8, 2 times 5 is 10. Once you've done that, you can then double back and actually check your work, because now everything has changed. Carbon, there's 8 and 8. Hydrogen, there's 20 and 20. Now when we get to oxygen, it's 2. We didn't change that one. But the other oxygen we did change is 16 plus 10, which is equal to 26. How can I get 2 equal to 26? I need to multiply by 13. There the number comes in. Okay, so it's recognizing those patterns to help you with those solves. This typically pops up, at least as far as Chem 130 goes, really in just combustion reactions. That's where it really comes in as a challenge. For those of you that are reviewing this video because of the lab, some of the lab questions for balancing, and maybe we should do it so you can stare me in the eye with daggers, are a lot more challenging. Okay, and it just kind of comes to a guess and check with how you float those numbers up to ensure they balance, and it's really coming down to a comfort with noting multiples. So if one side says 2 and the other side says 3, well, 6 is the lowest common multiple. Scale it up that way. Okay? And I know that doesn't sound very useful, but until you actually have a question that stumps you like that, it's not very productive to just kind of talk about it. You just kind of have to work your way through it. Okay? With that, I do think, oh, no, we've got practice here. So what you should be able to go through and do with all of these practice questions is determine the reaction type, predict the product, and balance the reaction. So reaction type and balance, you're always responsible for that. Predict the product, sometimes you are, sometimes you're not. But by determining the reaction type, you can now decide, is that predicting the product necessary? I will say that this is also a little bit skewed because I haven't officially talked about the double replacement and single replacement reactions in any real depth. They've popped up in that play posit, so it's going to be a little bit more challenging, but you should be able to go through and do it. So again, hit that pause button, stop the video, do whatever you got to do, try and solve these all out. And now that you're coming back after having done that, we should be able to try and piece them together. And because we've been doing it, I don't know, but I'm making weird noises too. Oh, that didn't work. There we go. Give you something exciting. So this first reaction, carbon, oxygen, CO2, and water, this is a combustion reaction. Because we are so good at balancing, we're able to recognize that that's going to be a 2, a 13, an 8, and a 5, right? For those of you going like crazy, remember we just solved that one. Okay. The next one, we've got text, so it helps to kind of write it out. A lithium metal, we should specify the phase, reacts with bromine gas to produce. So this is one that's saying, hey, I got to predict it. But that doesn't fit any of the patterns. That's not a single replacement. That's not a double replacement. What this looks like is a combination. Because it is a combination, I don't need to predict the product. And I therefore don't have to balance the equation because I don't know what the product is. Okay. The next one, it would be nice if I kept the color coding correct, was a decomposition, and I know it's a decomposition because it literally says this decomposes, which could mean that I would just stop right there, but let's go ahead. Sodium hydrogen carbonate decomposes. We usually see a little delta symbol over it. Because it's a decomposition, I don't need to know what that product is, so I don't need to balance it either. The next one, sodium chloride, aqueous, reacts with, so there's our plus, lithium nitrate, and aqueous. And looking at this, I have a metal and a non-metal, and I have a different metal and a different non-metal. This is fitting my double replacement reaction. I am expected to be able to predict this one. So I would exchange the lithium with the sodium. So I'd get lithium chloride plus sodium nitrate. Okay. Officially, those phases are things you need to be able to predict. But if you haven't recognized it from the video or practiced it yet, don't stress about that. Okay. One question that does typically pop up is that a student will go through and say, I wrote sodium nitrate plus lithium chloride. Am I right or are you right? We're both right. 2 plus 3 is 5. 3 plus 2 is 5. The order doesn't matter when we're looking at our addition, so don't stress about that. Both of those are perfectly valid. What is not valid would be lithium with sodium. We don't combine the same things, we combine the different ones. Okay, so that one's wrong. Zinc with lead sulfate. Hopefully we recognize we have a metal and a non-metal. We're looking at a single replacement reaction. We'll get the lead all by itself. And I forgot to label the other ones, but this was a single replacement. We're expected to predict products for single replacements, so we need to go through and show that. So we get the lead by itself as a solid, plus the zinc with sulfate aqueous, and so kind of carry the phases with those species. Again, order doesn't necessarily matter, though the lead will have to be a solid and the zinc sulfate will have to be aqueous. Again, we'll address that in, I think, the next video. Solid sulfur reacts with oxygen gas to produce sulfur dioxide. Didn't specify the phase, so I don't have to do that one. This would be a combination, and conveniently is already balanced for us. And then the last one, gold sulfate with copper by itself. That's a solid AQ. The gold sulfate one becomes a tricky one. I would be perfectly happy if you left it at AuSO4. Gold typically carries a +3 charge though. If gold is a +3, again, not expected to memorize that, but if we run under gold being a +3, what should that formula become? And we should get Au2SO4 3. Okay? And that one was also a single replacement reaction. Okay, so lots of different practice, lots of different pieces, color coding up the yin yang. Okay, so everything should be good there. So with that, we'll go ahead and say excellent job making it through yet another brutally long video where all I do is talk.